So, okay. All right. Anyway, sorry. Yes, my name is Cody Anderson. I am a Masters of Electrical student, but I work as a firmware developer. So, low-level assembly and all that stuff. Whilst it's not stuff I directly have ever had to use, it is quite useful to know for me. And it is an area that I have some expertise on, although I am by no means an expert. However, I'm going to try and teach you a little bit about that today. Okay. So in terms of why we're doing this, other than it's cool, this workshop series that we're kind of presenting is really focused around making an operating system or an operating system kernel, really. And in order to do that, you really need to know assembly. It's kind of like the glue that is going to bridge your C code to your computer, right? And so you need to write a little bit of assembly to get your operating system working. Ideally, you stick to C as much as you can, or now Rust is the new big thing, so you can do that as well, but you do need to write some assembly. It's also in general, it's just good to have an understanding of the level below what you're writing. Okay. If you're writing C code, it is just really handy to know assembly and have an understanding of how it works, because ultimately your C code is converted into assembly. So having an understanding of how it works and the limitations, it's just really handy. And lastly, assembly is kind of pops up in, well, it has and will continue to pop up in a lot of higher level areas as well. Like, if those of you who haven't heard, all the big web giants are coming together to make this thing called WebAssembly, which is kind of like, it's like JavaScript, but it runs a hell of a lot faster, right? It's code you can execute in your browser, but it's more around an assembly level, which means it can run a lot faster. And then, Java's converted to Java bytecode, C# compiled to the common intermediate language. These are all kind of assembly languages. They're not quite the same as the one we'll be looking at, but they're very similar in a lot of ways. So just having an understanding of what assembly is like, I think it's quite useful as a programmer. And so hopefully I can teach you all a little bit about that today. So to get started, we're gonna have to go through a handful of things, okay? But I've only got about 7 or 8 slides, okay? And then we're gonna jump into some code. So a lot of this workshop is practical. I'll be writing code and showing you things, okay? It may not all make sense straight away, but I'm hoping by the end I'll at least be able to, a fair bit of it will, sink in. I've had to cut a lot out as well. There's a lot to all of this, so I've done my best to condense it and make it digestible for people who are relatively new to this. But I do apologize if you miss anything. Feel free to ask questions or hang around at the end too. I'm happy to spend a bit more time talking about things. But yeah. All right, so to get started, let's talk about instruction set architectures. So we all hopefully know what a CPU is, okay? But if we have a CPU sitting in front of us, the question becomes, how do we actually program it, right? And so in order to do that, we will need to consult the instruction set architecture, okay? This is essentially the programmer's guide to a CPU, okay? It tells us what kind of instructions the CPU can execute, what the binary form of those instructions is, what kind of resources the CPU has available for us as a programmer to use. It's really the programming interface for a CPU, right? It doesn't specify any electrical details or how the circuits look. It just tells us how to actually program the thing. Okay. So, so some examples of popular ISAs are x86-64, which is basically what all of your laptops and desktop computers have. The processors inside them have the x86-64 ISA. Okay, so, the big processor companies, Intel and AMD, they make their own processors, but they all adhere to this ISA, right? If you write code for an Intel processor, it should work on an AMD processor as well, because they both follow the same instruction set architecture, okay? The circuits underneath may be completely different, okay? But the instruction set architecture is identical. So to the programmer, they are identical, okay? There's also ARMv8. So ARMv8's a really popular one for phones and tablets, and I've written tables there. Anyway, tablets, pretty much all your phones. Android is built to run on ARMv8, okay, and so is iOS. So That's all. Yeah, that's probably what your phones are using. Apple's also pushing towards having their laptops use ARMv8, so that's the Apple M1. And yeah, these are probably the two most popular at the moment, but they're not the ones we're going to be using today. Today, we're going to be using what's called RISC-V, so RISC standing for Reduced Instruction Set Computer. It's a relatively new ISA, relatively speaking anyway. It's still a few years old, but it's pretty new in this industry. There was a lot of research in its development. It wasn't as made quite as haphazardly as some of the others. I mean, ARM's relatively well thought out, but x86 is a bit of a nightmare. It's kind of just a hack tacked onto a hack tacked onto a hack. It's not, it was built as required, which has made it quite messy in its old age. RISC-V is kind of a bit different. It tries to keep things simple, okay? But it's still quite capable. You can run Linux on RISC-V. There is a Linux build for RISC-V that already exists, okay? It can compete with these, big ISAs. But yeah, it is a lot simpler, and that's one of the reasons we're going to be using it. So there's a lot of hype behind it at the moment. It's not used hugely yet, but a lot of the big companies are backing it. It's looking like, it's going to be useful in the near future, hopefully. These things do take time, though. We can, I mean, okay, you can use them at the moment, but like they're not heavily used. Sorry, someone in chat just pointed out that they may potentially be used, but not in any like huge numbers or anything like that. They're still, gaining traction. All right, anyway, we'll be talking about the 64-bit variant of RISC-V. That probably won't matter too much, but just as a note. Okay, so before we jump into programming, we need to talk about data storage specifically. So when we're working on, when we're writing a program, right, usually a program's job is to manipulate data in some way or some form. That might be real-time data coming in from, sensors or something, or a keyboard. It might be data stored on a hard drive, right? But ultimately, we want to manipulate data. And so in order to manipulate data, we need to have it stored somewhere, okay? So there are sort of two places that the processor stores data that it's currently working on. One of these places is memory, or main memory, as it's sometimes called, or just RAM, which is random access memory. Has many names, but anyway, the way memory works is it's effectively just a giant array, okay? And so you have, you have a big ass array full of bytes, okay? So at each address, you have a single byte of data stored. And so I can ask for the data stored at address 2, and it will give me 1, or I can change the data stored at address 2, and then any subsequent calls to that address will give me the data stored there, okay? So each slot in memory is 1 byte, so it's 8 bits, all right? It can store a number between 0 and 255, all right? Now, obviously, we like to use bigger numbers than this. So if we want to store a bigger number, okay, we can use multiple slots or multiple addresses. So the C integer is usually 32 bits in size. So you can see it takes up 4 slots. 32 bits is 4 bytes, right? And yeah, so in this example here, we can combine all of these numbers together, and that represents the decimal number 65,545, which in hexadecimal is this number here. As you can see, it's pretty easy to convert between the individual bytes and the final representation in decimal, hexadecimal. You just kind of put them all together. You've got the 9 here and the 0 here and the 1 here. That's kind of why we use hexadecimal. It's much easier to read memory and data when it's stored in hexadecimal. So, and that's why a lot of what we'll be doing from now is stored in hexadecimal. But yeah, so that's main memory. It's just a big array of bytes, okay? And we can store arbitrary data there, okay? The problem with main memory is we can't really do any work on it, okay? We can store data there, we can read data from it, but we can't like add to it. We can't say add 3 to address 1. That's just not something most computers can do. There's probably some exceptions to that, but we're not going to focus on those. So in order to manipulate memory, we need to first load the data into registers. Okay, so RISC-V has 32 general purpose registers, okay? And they're labeled X0 through to X31, okay? When we're writing assembly, we can also refer to them by their ABI name, all right? So these are just handy mnemonics that relate to their kind of function, I suppose you could say. But ultimately, it's just easier for us as if the ABI names are just for convenience, okay? All of the registers are identical, okay? They can all store a single 64-bit number, okay? That's, you know, because this is the 64-bit variant, and 32-bit variant, they can store 32-bit numbers. But yeah, so yeah, we have, yeah, sorry, lost my train of thought. So yeah, 32 64-bit registers, all right? There is one exception. X0 is always 0, okay? No matter what, you can't change the value. If you try to change the value, nothing happens. It just stays 0, okay? Okay, so when we have registers and we have memory, okay? In order to use this practically, what ends up happening is, so a typical sort of flow for manipulating some data is it'll be in memory, okay? And we'll load it into a register, okay? So we've got this memory at address 100. We'll put it into register X1. We've got another piece of data at address 300, and we'll put it into X2, okay? And then we can use, for example, the add instruction on them, okay? And so this instruction sets X3 to the value X1 plus X2, okay? Now we have the data in X3 and we can store it back into memory, okay? So that's how we go about manipulating data, right? We have very limited registers, right? We only have 32 of them, so we need to make use of them, but we have huge amounts of memory. So we will load some data in temporarily, do some operations on it, and then put it back when we're done with it. You don't necessarily have to put it back straight away. You know, we could do more with this X3 now. We could add another register to it or something like that. But yeah, that's sort of how the general CPU does things. It loads stuff from data, operates on it. It loads data from memory, does some operations on it, and puts it back. There is one other way to kind of put numbers into registers. So obviously putting everything into memory is a bit overkill, right? There are some special instructions that can that take intermediate arguments, okay? So that just means that the argument is encoded as part of the instruction. So for example, the load intermediate instruction takes one register and a number, okay? And it basically will store that number in that register, okay? And so this instruction, load intermediate x15, will always load the value 5 into x1. That's all it does, okay? It doesn't matter what set up in memory or whatever, right? Whereas when we're loading from memory, it depends what's at the memory address. The load intermediate will just always put 5 into x1. And we also have an add intermediate, which takes 2 registers and a number. So it will calculate x3 equals x1 plus the number you give it. In this case, it's 1. So you can imagine adding 1 is a very common operation. So it's convenient to just be able to do it in one instruction rather than having to load 1 into a register and then add it. So yeah, okay, cool. So that's pretty much all we have to cover for the basics. We're going to write some actual code now. So let me just jump across to my code window. 2 secs, guys. And don't worry if not all of that made sense. I'm hoping it will all come together a little bit better when we start actually writing some code. Cool. Okay, so yeah, so we have here a relatively empty window. I just got some pictures and stuff to show you later, and I've got a linker script. We're not going to talk too much about this, but you do need it. If anyone's curious about this, I'm happy to go through it at the end, but it's just, there is a lot of content here and we have to cut some out, unfortunately. But we're going to start with a really simple example, okay? And so when we're running assembly, we use the .s extension. So hello.s is going to be our file, okay? .s or .asm are the usual file extensions. And we're going to just sort of, we're going to take it very slow to start with. We're just going to use the assembly to just kind of put some data into memory, okay? Assembly files are very close to like binary, okay? They're kind of just handy ways of writing like binary files, really. So we can do something like bytes, which is a command in the assembler, and 1, 2. And this basically just tells the assembler to put the numbers 1 and 2 in sequence into memory. Okay. And we can put some more bytes into memory, 3 and 4. Okay. We also just need to put this. I'll explain this in a second, but just take my word for it. We need that. But yeah, this is an assembly file for RISC-V. It doesn't do much. In fact, it doesn't really do anything. It doesn't even define code. It just tells me to, just says to put some data into memory. But we can compile it. And so we have the compile command here. It's quite long. Again, I'm not going to go through it. We are using GCC, all right? And this is like a build of GCC for RISC-V, okay? But in terms of what all the arguments are and stuff, again, they're on the GitHub. They're not super complicated, but I just don't want to spend too much time going through them. So just take my word for it. This is the compile command we're going to use. Oh yeah, I have to put a new line at the end, otherwise it complains. And yeah, cool. We did get one warning, but forget about that. So we've got our output. Okay. Now let's take a look at our output and see what it is. Right. So this is the output file we're using object dump, which is again a standard tool as part of the GCC toolchain. It just shows us basically some more information about the output binary. Okay, and we can see here we have this section called .text, okay, which is correlates to this, right? So when we write .section.text, we're telling the assembler to put our code in the text section, okay? And you can see here, we've laid out the numbers 1, 2, 3, and 4. And so we've got here the numbers 1, 2, 3, and 4, right? If we were to change this to a 6 and recompile, we would get 1, 2, and a 6 here instead, okay? Yeah, so we put it in the text section because we asked to put it in the text section. Okay, we can put some other data in a different section. So for example, row data is another section we can use. If we compile and run, oh, whoops, what I do? Sorry. Oh, right, I didn't actually put any data in there. Yeah, so we can put some other stuff like 8 and 9. Okay, we compile, line at the end, compile, and we run. We'll see we now have 2 sections, okay? So sections are just a way to split up the binary a little bit. They're not super relevant to what we're doing here, but basically they're just, if you have multiple like assembly files and you want to bring them all together, then you use the dot sections to kind of group similar things. So for example, the row data section is used for read-only data. Dot text is typically used for code. Okay, and that's all actually defined in the assembly script here, and sorry, the linker script here. Okay. So yeah, we can see too that this is the address here where it's going to be stored. Okay, so it's stored at 80 million. We told it to store it at 80 million in the linker file. There's a reason for that, but again, it doesn't really matter. But you can see here we've got our 4 bytes, and then the contents of row data is going to be stored at 80 million and 4 because it's, because we can't store it at 80 million, so we're going to store it at the next available address. Okay. So yeah, and we can add in more data and stuff like that. But that's kind of the basics of how assembly works. We're really working quite close to the raw binary level. Okay, we can just throw random data in. Okay, so now we'll try writing some actual instructions. All right, so if we get rid of all of that, and we'll use a really simple instruction. So the LI, which is the load intermediate instruction from before. Okay. And we're just going to load the value 1 into x5, okay? And so if we run the compiler again and we look at the output, we can see, oh, sorry, let's put a bigger value in. So yeah, if we run the compiler again, we can see the contents of the dot section now. We have some other number, okay? And it's at address 80 million, again, our starting point. So this other number, it represents the instruction here, Okay, now it's not very readable here, but we can tell object dumped to disassemble the code. And instead it will tell us the instruction. So you can see that this number here corresponds to this instruction, which is the instruction we asked for. Cool. The disassembler is using T0 instead of X5. So if we look at the register page, X5, the ABI name is actually T0. So it's just a synonym. You can use X5 or T0. The assembler prefers T0. We're probably going to prefer ABI names as well, but either is perfectly fine. They mean the exact same thing. So yeah, if we put T0 here instead and recompile, you'll see it still says T0. It's the same thing. Okay, cool. So if we put another line and put some more assembly, maybe we'll add, oh, sorry. So if we use add-I instruction and we add, I don't know, 50 to it. Okay, so this is just saying T1 is equal to T0 plus 50. All right, and we save and compile again. We'll get 2 instructions this time, right? So yeah, that's pretty straightforward. And if we look at it in this mode again, we'll see that we have we have a little bit more information in our doc text, okay, which corresponds to our 2 instructions. All right. Also, there is this section which is just added by the compiler. Don't worry about it. It doesn't mean anything. It's just some metadata the compiler adds. It pretty much gets thrown away straight away. But yeah. Okay, cool. So that's kind of the basics. Now, there is one other thing we should cover when we're just talking about like basic structure of these files, okay? And that is labels. Now, labels are super important. They're pretty much the main reason you want to use an assembler as opposed to just, you know, a really simple tool, okay? Labels keep track of addresses for us, okay? So you can see these 2 numbers are stored, or this here is stored at 80,000. Now this one's actually stored at 80,004, all right, because it's after this one, okay? They can't both be stored at the exact same address and they're both 4-byte numbers, all right? So how do we reference back to these addresses though? Because, you know, obviously if I wanted to, for example, go back to this instruction and form some kind of loop or something, I don't want to have to type in 80,004, right? I don't want to have to count down instructions and figure out where I'm at and stuff like that. That could be really difficult. So instead, I can put a label in and I'll just call it, I don't know, loop, right? Now, what it does, the label, it doesn't modify the output at all, okay? If we look at the output, it's still identical, okay? But if we look at the disassembled output, we'll see that the disassembler has kept track of this label for us. And so it has said that loop is this address, 80,004. It's laying out the code slightly different. We've still got the same 2 instructions, okay? But it's now telling us where they are relative to these labels, okay? So these labels are just ways of keeping track of positions within the binary, all right? And we'll reference those labels back later when we need to refer to specific positions within the binary file, okay? We could also, a particularly useful example is if we wanted to store some data, we could use a label and then do byte and then, you know, put our data here again, right? And then again, this isn't like, I mean, this will obviously add some data to the output, but the labels, yeah, so we've got our 1, 2, 3, 4 at the end. And the label data is just going to tell us where this is, okay, so that we know, because otherwise, you know, if we want to be able to use this data, we need to know where it's stored. And we don't want to have to, again, count addresses and figure out exactly where it is and then hard code the address. Instead, we can just use the name data. Putting the underscore in front is a convention, by the way. You don't have to. It can be anything that's not like a keyword for the assembler, but yeah. Anyway, so okay, so that's super basics of assembler. So now we're going to start with a super quick actually running a program. Okay. So our linker script is set up so that start is considered the start of the program. Okay, it will actually make sure that start is at the very start. So that's all that label means. And let's print something. Okay, so let's print the letter H. All right. So to print the letter H, all right, we're first going to have to load some data into a register. We're going to have to load the H, okay? And we're going to do that like this. Now, what this is saying is it's saying load H into register T0, okay? But obviously we can't actually load a letter into a register. So this is going to load the ASCII representation of H, okay? So this will get converted to, if we look at our ASCII table here, it will get converted to the number 104, or which is 68 in hexadecimal, okay? So this is the same as 104. All right, and if we actually compile this, what have I done? Li T0H, T0H, what have I done? Oh, bad expression, division by 0, interesting. Oh, right, comments. Yeah, cool. Sorry, wrong comment character. Yeah, there we go. And then we, what am I, wait. Okay, yeah, never mind. Okay. Anyway, and then we look at our disassembled output, we'll see that it's actually loading the number 104, not H. So the assembler just converts that. It's just a handy thing for us. Okay. So the next question is, how do we print? It's a very good question because we don't really have any hardware connected to. We're going to be simulating a RISC-V processor. We don't really, connecting to monitors and stuff and showing images is quite complicated. We're not going to do that. Instead, we're going to store the value at a particular address. So if we store numbers at this address, okay, it will print them out as ASCII characters. There is obviously a reason why this happens, but I don't want to go into it. We're just going to use this for debugging purposes and to make some more visual demonstrations of things, okay? So, yeah, oh, sorry, hold on 2 seconds, guys. Okay, cool. So, yeah. So we've loaded H into T0, okay? Now we want to store it at this address, okay? So in order to store something at an address, what we're going to do is we're going to use the LA instruction, which is load address, okay? And we're going to load it into register T1, okay? And we're going to load this. Again, this is an intermediate value, so this value becomes part of the instruction. This instruction will always load this address into T1, okay? And then finally, we're going to store a value there. So we'll use the SB instruction, store byte, okay? And so we're going to store the value stored in T0, okay, at the address of stored in T1, okay? And so this little notation here is just because the store byte allows us to specify an offset, okay? So if we wanted to store at, this address +1, so here, right, we could actually just put a 1 here and this would offset it by 1, okay? But we're not going to be using that. We're just going to put a 0 there. So we're going to store it exactly at the address stored in T1, which is what's like 1,000,000, yeah, 10 million. Okay, cool. So let's compile that. Oh, what have I done now? I put another dodgy comment. Yeah, okay. Cool. And we're going to have a look at it. And you'll see our instructions are here. The assembler is actually pretty clever too. It's actually figured out that we've put this particular address in T1 because, again, we're using the LI instructions. So it knows exactly where we're storing it. It's telling us it's at start minus this amount, which is, relative to the start label. The LUI is actually because this instruction gets converted into a load upper instruction. We're not going to talk about this too much again, but this instruction is not actually a real instruction. It's called a pseudo instruction. The assembler will turn it into a real instruction for us. It's just that it's not always super straightforward to load addresses in RISC-V. So this LA instruction is like a handy thing that the assembler gives us, but again, that's a bit complicated. We're not going to worry too much about that. The important thing is it loads the address we want into T1. Okay, cool. So we got our code. How do we run it? Again, I'm not going to go through. So the program we're using is called QEMU. Okay, it's a really handy program. It can simulate all types of different processes. we're going to obviously be using it to simulate a RISC-V processor. The command's quite long. It's not actually super complicated either, but I don't want to go through it. It's not super relevant. Just take my word for it. This is going to simulate a RISC-V processor. Oh, sorry, guys. People cooking in my house. Oh, God. Hold on. Sorry. There. Let me just. Okay. Sorry about that, guys. Housemates. Anyway. So yeah. If we run this, it simulates our processor and we see it prints out a H. Cool. And we'll just kill it. And yeah. And so how could we print out a little bit more of a complete example? So we can actually just copy and paste this line a bunch of times and change the letters, right? So we can load E instead and then L and L and then O. And we have a super basic, we have a super basic hello world program. So yeah, that's how you assembly, I guess, at a very basic level. So this is not an ideal program, obviously. There are a lot of issues with it. Like we don't want to have to repeat the line to print out each character. And really, we would want to print out a string from memory, right? Not just like these hard-coded letters. So we're going to move on to a slightly more complicated example where we actually try and build a loop, okay? And we'll read out some data from memory and print it out. All right, so we'll ditch all this except for the address because we're still going to need that special address. And we're going to start by introducing something new. So in the read-only data section, we're going to put some data in. We're going to put a string in, all right? And so using the .string command, this will basically put a string into memory encoded as an ASCII string, very similar to the way it put the bytes in, okay? So it's really just taking each character, converting it to its byte, to its code, its ASCII code, and then storing it into memory. Does it automatically send it to the next available? Sorry, I'm a bit late on reading questions. What was that for? The automatically send it to the next available address. What was that?
That was for the question. Let me just write it out. How are you able to save each different character to the same memory address without offsetting?
Oh, okay, yeah. So that was that for when we were printing before the hello. Yeah. So again, that memory address is special. We're not going to talk about it. I'm happy to talk about it at the end, but just not in the middle. It's quite a bit of depth there, but basically certain sections of memory do special things. That in particular one, whenever you store something there, it will print it out. Okay, so it prints it out immediately, so you can just keep storing characters there and it'll keep printing them out. Okay, and so that's the mechanism we're going to be exploiting today, just to show. Yeah, it's like PutChar, exactly. It's really, and even then we're not actually using it properly, but we're just abusing the fact that this is all simulated to get away with an easy way of doing it. Yeah, bootleg PutChar, exactly. Okay, so yeah, we're gonna put some data into the raw data section. Okay, and so we've got our string here, hello world. Okay, again, the assembler is just going to lay this out into memory, each byte in sequence. Okay, and then straight after that string, we're going to put a byte 0. So those of you who are familiar with C will know that strings are terminated by a 0. So we're going to use this 0 to detect the end of the string. Okay, none of these ASCII characters will get converted into a 0. So we're all good there. All right. And just, for interest, we can compile it and have a look at the data, and we can see now we've got a little bit more data. The object dump tool is actually going to show us the ASCII representation of this data as well. So if you can see the hello world string in there. And yeah, we've got our single instruction, which is just to load this address into T1. So yeah, we've got some stuff in there now. So yeah, okay, cool. So now we got to write the actual program, obviously. Oh, you know what? I just realized why this warning's coming up. don't worry about it. So yeah, okay, no, we won't worry about it, doesn't matter. All right, cool. So yeah, let's get started. So to start with, we're obviously going to load this address because we're going to need it. We'll put it in T0 this time. Doesn't actually matter which register we put it in, but we're going to put it in there because that's what my notes did. And we're going to load the string. So to load the string, we're not actually going to load the string itself. We're going to load the memory address of the string into T1. Okay, and so we can do that by typing this here. Okay, and so the assembler is going to replace this string with the actual location in memory of the string. Okay, so this is where we actually start to use labels in their practical sense. Okay. And so we're going to load the address of the string in this register to kick off our loop. All right. And so this is kind of as a C code equivalent. This is sort of just like saying T1 is equal to @_string, right? We're just storing the address. Okay. So, all right, let's kick off a loop. So to start with, we need a label to denote the start of our loop. Okay. We need to be going back to the start to loop. Okay, so we're going to use this label. All right, and so you can kind of think of this as the start of our loop, right? So it's like while, and we're going to be doing a kind of dodgy loop, so it's sort of equivalent to while one. Yeah, and now we're going to do we're going to load a character of the string. Okay, so we've got the address stored in T1, but now we want to actually load a character, right? The address doesn't do us much good on its own. We need to know what's actually stored there. So we're going to use the load byte instruction, okay? And so the load byte, we will load into T2 the value stored at the address in T1, okay? Again, this is an offset. We can use offsets. We won't be using it here, but you can offset your loads as well. And so this is kind of equivalent, well, it's pretty much equivalent to saying T2 is equal to T1 with the dereference operator for those, again, who knows C. All right, so yeah, we're loading the very first character into T2, okay? Now, we need to check if it's 0, right? We're denoting the end of our string with a 0. So we want to break the loop if we see a 0. So we're going to use this branch if equals command, okay? And we're going to be checking if T2, which is our character, is equal to x0. Now, you may remember from our registers, x0 is always 0. So we can actually also use the ABI name, which is just 0, x0 or a 0 or 0 are synonymous. We'll just stick with 0 because it's probably a bit easier. But yeah, what we're doing here is we're comparing these two numbers, and if they're equal, okay, we're going to jump to a label. Now we need to put another label at the end here just so that we have somewhere to jump to. And we're going to say, if you are equal to 0, jump to the end, okay? And yeah, this is our bootleg if statement. Bootleg goto. No, this is an actual goto, but it's kind of equivalent to T2. If T2 is equal to 0, we will break. Okay, or you could also, if you're familiar with goto, this is kind of like goto end here. But anyway, that doesn't matter. So yeah, same thing. Okay, cool. Now we've checked if it's 0, so it's not a 0 character. So we want to actually print it again. Like we did before, we're going to store the byte stored in T2. We're going to store it at the address that is stored within T0, which is where we put that special address. And yeah, I think that's most of our, so this is kind of, yeah, like our PutChar from before. So we're kind of doing a PutChar T2, right? And then finally, we need to change something, right? Because we need to loop, okay? If we don't change anything about the kind of state, we're just going to keep looping and loading the same character. So we're actually going to increment the string address. So if you remember, T1 stores our string address, okay? So it started at _string. So we're just going to increment it. So we're going to use the add-I instruction, okay? And we're going to take T1 and make T1 equal to T1 plus 1. Right? So we're just incrementing the address here. And yeah, we have T1 plus 1. So now we're looking at the next character. And then to finish off the loop, we need to jump back to the start. So the jump command, jump _loop, is just going to move execution back to line 15, right? So we're just going to jump back to the start of this loop and do it again. Any kind of anonymous labels. Okay, so yeah, so the question was, does the assembler have any kind of anonymous labels? So, all right, so unless you specify using the .global command, global, and so we actually should be using .global start because start is a global, then all of these labels will be local to this file, okay? They shouldn't pollute the space. However, there is also these special ones. You can actually, oh shit, as part of risk 5, you can also use numbers as labels, okay? Now, when you use a number as label, and if you want to jump to that label, you actually need to go type the label number and then whether it was before or after. So if you do 1B, is it 1? Maybe it's not B. Anyway, maybe a better example is if you put a label 1 here, you can actually do jump 1F. Oh, okay, it's just not syntax highlighting. Never mind then. This is saying jump to the next label that is 1, okay? And then you can also put 1 here as well. And so that one is 1B because it's behind this instruction. So yeah, you can do those. Don't worry too much if that didn't make sense, but you can do these local labels using numbers. It's a bit weird, but yeah, it's pretty handy at the same time. The assembler uses it. The C compiler uses it heaps when you look at the C code. But yeah, okay, cool. So I think that's pretty much it. So this should loop through our string, and so this jump kind of seals off our whole code. And then I'm just going to put a wait for interrupt instruction. That's basically just going to pause the CPU. It does a bit more than that, but don't worry about it. I'm just going to put it at the end because otherwise things get a bit of a pain. But yeah, we're all good. So now if we compile it and get a complaint because there's no new line at the end, that's really important apparently. And then we'll have a quick look. We'll see that we've got a little bit more code there this time. And if we look at the disassembled output as well, we can see all of our instructions and all of our labels nicely kind of laid out. Okay, and now we will finally run it using QEMU, and it prints hello world. So that is a much nicer way, even if it's a bit gross. This can print out arbitrary strings. I don't have to completely rewrite the code. I can just add a bunch more characters and then recompile and rerun it. And yeah, we get our changes. So yeah, this is kind of roughly how your loops get translated into assembly, okay? Your C compiler obviously does all this for you, but ultimately this is sort of what loops look like. Yeah, okay. Oh wow, it is 7:50 already. Damn, this took a lot more time than I thought. Okay, we might skip the next example then, and we'll just go to the last example. Maybe I'll go through the next example if we have time, but it's not super important. We'll instead skip to the last example. So the last example here, we're going to start to pull everything together. We're going to actually interact with C. So I'm actually going to be writing some C code as well. So let me make a new hello.c file. And yeah, I think this is probably the most interesting part, okay, is understanding how C ties into all of this and how we can actually, match our assembly in our C code. Okay. So we'll start with a super simple example, all right? We'll just kind of do the absolute bare minimum to get some C code running, all right? So to do this, we will need to put some data in the data section, okay? Data section is used for write data, I guess, not read-only data we can actually modify. I was actually going to recommend Godbolt at the end, but anyway, sorry. So yeah, we can put actual data in the data segment, all right, data that we want to modify later. And so what we're going to do is we're just going to put, oh wait, what the hell? Oh, okay, I don't have it here. We're just going to do dot zero, which will just put a bunch of zeros, okay? And we'll just put, I don't know, 1,000 zeros into this data, okay? And so this is going to be our stack. So the main thing we need to set up for the C program to work is we need an area of memory. We need to allocate an area of memory for it called the stack. All right. The stack is like the working area for C. It stores a lot of temporary values there. This isn't a C programming course, so we're not going to talk about what the stack is and what it looks like. But I'm just telling you, we do need to give it some space to put the stack, okay? And so that's what we're doing here, all right? All right, and so what do we do with this memory though? How do we tell C where this memory is? Well, if you go back to our registers, okay, this is where we start actually looking at the ABI, okay? So the ABI is how the registers are used by C, all right? And so, for example, X2 is the stack pointer. So X2 is where we need to put a pointer to the stack. Pretty straightforward. So we're going to load address into our X2, which is synonymous for SP. If you remember, we can use either the register name or the ABI name. We'll stick with ABI names. It's a bit easier. And we're going to put stack in there. Okay. Now, this isn't quite finished though, because we actually need to put the bottom of the stack, the last address of the stack in. So there's a few ways to do this, but for simplicity, I'm just going to add 1,000. So yeah, we could, yeah. And this will basically, the assembler will calculate this part on its own, by the way. This isn't done by the assembly, but it's just a convenient thing for us. So the assembler will output an instruction that stores the last address of the stack into stack pointer, okay? It's just the way the stack works. Again, this isn't a course on stack, but there's plenty of good material on how the stack works if you're not familiar with it. Okay, and now that we have our stack set up, that's literally all we actually need to get started with C. So we can jump into our main function. Now we're going to define the main function in the C file, so that's not here. But yeah, this is really the minimum we need to get C working from assembly. It's actually not a lot. Okay, and so now we can jump over to our C and we can make a new function, void main. And yeah, this here will actually jump to this function here and it will start executing it. Now we haven't given it any arguments and we are not using the return value. So all of that's just void. And this, since we don't have any standard libraries, this kind of leaves us with not a lot to do. But you know, we could put some code in here and make it int x equal to 5 and do a bunch of other things, right? But yeah, you're gonna have to take my word on this example that this works. So it does. But moving on, let's maybe give the function some arguments so we can actually do something. So in particular, I would like to pass that special address to the C code so that we can actually start printing some things and seeing it working. Okay. Now, in order to pass arguments to the function, okay, we again look at our ABI descriptions for our registers, and we'll see that x10 or A0 is the first function argument. All right. So what we can do is we can load our address into A0. And now we can actually add an argument to this function. Okay, so I'm going to make it a volatile character pointer. Shit, I spelled, oh no, volatile. No, that's fine, I think. Yeah, we'll call it UI because that's what it is really, but don't worry about the name too much. But yeah, now C will actually receive this argument. Now, something to understand here is that if I didn't put this line here and I still put this line here, okay, C would just take my word for it, assume there's an argument in A0 and use it, okay? There's no real checking here to see that everything's all lined up, okay? I'm also just telling it it's this type. It could be anything, okay? It could be literally, yeah, it could just be a simple number. It could not actually represent an address. It's all binary at the end of the day, all right? But when we get into C, C starts enforcing types, okay? And so we need to tell it what this data is going to be, all right? And I am going to say that it's a char pointer because we were storing characters at it, right? It's volatile. Again, it's not super important why it's volatile, but we need to tell it to be volatile so that the compiler optimizations don't completely ruin our code. And yeah, and so now with all of that out of the way, we can finally do a really simple test. Again, let's go back to storing H, okay? And we can dereference UART and store H there, okay? And so I think we're all good then. We can run our compiler and we just need to add our hello underscore c.c and it compiles and then we run qemu and we see it prints h. Interesting that you do reference pointers that way. Well, I mean, this is a pretty reasonable with the, oh yeah, the brackets I think is a, yeah, sorry, the question in chat is it's interesting that you dereference pointers with brackets around it. You don't have to, you can do it like this as well. It's just a habit. I don't know, I see a lot of systems programmers do that. I'm not 100% sure why I picked it up as well, but maybe it just, yeah, anyway, probably safer or something, I don't know. But yeah, anyway, so we can, yeah, and then if we want to, again, mimic our example from the first one, we can put our full hello here. And we'll see that if we recompile, we get the full hello. Okay. And just to kind of put this example even further, I'm not going to write this code out. Again, this isn't a C programming class, but I do have a bit of a example print here. So we could write a function instead, and we'll need to take that URT here because I sort of skipped some steps. Put a function here, and we can write our very own print function. This should be called plot, my bad. And now, instead of doing all that grossness, we can just say hello. Chuck a new line there. And then is that all good? What have I done? Why is it complaining? I missed something.
Need the second argument for the URI address.
Oh, yes, of course. Yes, sorry, you're right. I didn't put UI at the start of that. Yeah, okay, cool. And now it's gonna, no, okay, now it's all good. Yeah, cool. And then we compile that and we run it, print hello, and we can reuse our print hello function a bunch. Okay. And print some other things, right? Yeah. Also, if we investigate the binary a little bit, oh, that command's going to be a while up, isn't it? We can actually see the, oh yeah, there's a lot more stuff here now. We can actually see all of our strings stored there. So C is storing its strings in the row data section as well. So you can see that standard. It's also putting its code in the text segment. It doesn't have any data. So it also has, yeah, comments. So it's added its own section for GCC. Again, these last two sections really don't do anything in practice. They're just for a bit of metadata. But yeah, okay. I didn't want this to really go over an hour, so I'm just going to do one more quick thing related to this example, and then after that, I'll probably just kind of, if people want to know anything else or whatever, we'll hang around. We'll probably stop the recording. I've got another example I can go through if you're interested in or something like that. But yeah, I just want to keep the main section to an hour, so we'll just run through one other quick thing, and that is we're going to look at kind of the flip side of how do we call assembly from C. So it's very similar, but a few differences. So what we want to do is make a, we want to make a function for our C code to call. So a particularly useful one is probably going to be a PutChar function, right? So rather than actually passing this address into C, we can just give C an easy way of printing an individual character. Okay, so let's start with how we tell, well, sorry, let's start with what we have to put into C. Okay, so what we really want is we want a void function that takes a single character argument, okay, and then prints it, all right? So this is what we're trying to build, all right? So, I mean, there's no return argument, so that's pretty easy, but we do need to take that argument. So again, C is going to use this ABI. It's going to put the first argument in A0, okay? So we know that our char is in A0, okay? And so we just want to print it. So we're going to load an address, okay? We're going to load this address we need into T0. We can't assume that the registers have any values that we previously set up or anything in it. When we get into this function, we basically kind of need to assume that everything's empty. All right. We can assume the stack point is present, but we're not going to use the stack because that's a little bit confusing. But yeah, C doesn't make any guarantees about saving any registers for us or anything like that. So as far as we know, all the registers have garbage in them. Okay. Except for A0, which has the argument we want. Okay. And then again, like we did previously, we're just going to store A0 at the address in T0. Okay. Last thing we need to do is we need to return. Okay, so we're going to use this special instruction JumpReturn, okay, or jump register, sorry, which jumps to the address stored in a register, and we're going to jump to the RA register, okay? The reason being is, again, the RA register is the call return address. So C will store the return address needed into the RA register. All we have to do is jump to it. Okay, so this here should represent the function we want. One last thing, in C, we do actually need this definition, and we need to write extern. We're just telling C that this function is declared elsewhere, but you can use it. Okay, and in hello.s, we just need to tell the assembler that PutChar is a global symbol, so it needs to, you know, it should keep it around. Other things may be using it. Okay, cool. Also, I'll just chuck that wait for. Yeah, it doesn't. We won't worry about that. Something weird might happen, but anyway. Yeah, and so instead of this line here now, we can use our PutChar function and just put C. And that means we can get rid of this UART, and that means we can get rid of it here as well. Oh, whoops, there we go. Okay. And so from here, if we run the compiler one last time, yes, new line at the end, yeah. We run our compiler one last time and we run the output, we'll see all of our hellos are still intact, but instead of using that address and doing it ourselves, we're calling our handy PutChar function. And just to really hammer home that this is working, we can throw in a little fun thing where we, after every character, we throw in something, an exclamation mark. So if we recompile that and we run it, we'll see it throws exclamation marks after every single character it prints. Yeah, okay. I think that brings us to the end. I don't know if there's anything else super important I wanted to cover. Oh, we can also, if we just to sort of, we can use that return address thing as well. So if we load address and we load end into RA, then when the C code is done, it will come back to end. Okay, so we're putting a return address into the return address register, and then C will jump back to the return address, so it will come back to our code. But yeah, that's just a minor note. But yeah, all right. Were there any final questions? No.
All right, I'll stop recording.
Yeah, cool.